Hello there, and welcome to the Sleepy Library. I'm so glad you found your way here tonight. If you're settling into bed, adjusting your pillows just right, or simply looking for a quiet corner of the internet where science becomes a gentle lullaby, then you're exactly where you need to be. Tonight, we're going to journey back in time, further back than you can possibly imagine, to the very beginning of everything. We're going to explore the Big Bang Theory, the story of how our universe came to be. So, take a deep breath. Let your shoulders relax. Get comfortable. Long before there were scientists with telescopes and particle accelerators, before there were philosophers pondering the nature of existence, there was the sky. And humans, throughout all of history, have looked up at that sky and wondered, where did all of this come from? How did the stars get there? Was there a beginning? Or has the universe simply always existed, stretching infinitely into the past and future? These are questions that have haunted humanity since the first person looked up at the night sky and felt that peculiar mixture of wonder and smallness that the cosmos inspires. For thousands of years, these questions belonged to the realm of mythology and religion. But in the 20th century, something remarkable happened. Science, which had been quietly studying the universe through increasingly powerful instruments, began to piece together an answer. Not a mythological answer, but one based on observation, mathematics, and evidence. The story begins in the 1920s, in an era when physicists and astronomers were beginning to realize that the universe was far stranger and more wonderful than anyone had imagined. The early 20th century had already brought us quantum mechanics, revealing that, at the smallest scales, reality behaves in ways that defy our everyday intuition. It had brought us Einstein's theory of special relativity, showing that time and space are not absolute, but relative, depending on one's motion. And then came general relativity, Einstein's masterwork, which described gravity not as a force, but as the curvature of space-time itself. A Belgian priest and physicist named Georges Lemaitre was thinking deeply about the nature of the cosmos. This might seem like an unusual combination, a priest who was also a physicist, but Lemaitre saw no contradiction between his faith and his science. He believed that understanding the physical mechanisms of creation was a way of appreciating the grandeur of the Creator. He had studied Einstein's equations of general relativity, those elegant mathematical descriptions of how space and time bend and curve in the presence of matter and energy. And as Lemaitre worked through these equations, he came to a startling conclusion. If the universe was expanding, as some observations were beginning to suggest, then running the clock backward would mean it was once smaller, much smaller. And if you kept going back through time, the universe would get more and more compressed until, at some distant point in the past, everything that exists today, every atom, every particle, every bit of energy in the entire cosmos, would have been squeezed together into an unimaginably dense, hot point. Lemaitre called this the primeval atom. He imagined it as a kind of cosmic egg, containing all of space, time, matter, and energy in a state of incredible compression, waiting to hatch into the universe we know. This was a radical idea. Most scientists at the time assumed the universe was eternal and unchanging on the largest scales. Even Einstein, whose equations Lemaitre was using, initially resisted the idea of a changing universe. Einstein had actually modified his own equations by adding something called the cosmological constant, a mathematical term that would keep the universe static, neither expanding nor contracting. He believed so strongly in a static universe that he was willing to add this extra term, this fudge factor, to make his equations match his intuition. But around the same time, an American astronomer named Edwin Hubble was making his own groundbreaking observations. Hubble worked at the Mount Wilson Observatory in California, home to what was then the most powerful telescope in the world, a magnificent instrument with a mirror 100 inches across. Night after night, Hubble turned this telescope toward faint, fuzzy patches of light in the sky that were called nebulae. Some astronomers thought these nebulae were clouds of gas within our own Milky Way galaxy. But Hubble suspected they might be something much more extraordinary. Using a technique involving special stars called Cepheid variables, stars whose brightness pulses in a regular, predictable way, Hubble was able to measure the distances to these nebulae. And what he found was shocking. These weren't nebulae at all. They were entire galaxies, vast collections of billions of stars, lying far beyond the boundaries of our own Milky Way. The universe, it turned out, was much larger than anyone had thought. Our galaxy was just one of countless galaxies scattered through space. But Hubble didn't stop there. He also measured something else about these distant galaxies. By analyzing their light, using a technique called spectroscopy, splitting the light into its component colors like a rainbow, he could identify specific patterns, signatures left by elements in the stars of those galaxies. And he noticed something peculiar. These patterns were shifted toward the red end of the spectrum. This redshift, as it's called, happens when a light source is moving away from you. It's similar to the Doppler effect you hear when an ambulance drives past, its siren dropping in pitch as it recedes. Light from distant galaxies was shifted to redder, longer wavelengths because those galaxies were moving away from us. And here's the truly remarkable part. The farther away a galaxy was, the faster it was moving away. The more distant the galaxy, the greater its redshift. This wasn't because we were at the center of some cosmic escape, with everything fleeing from Earth in particular. No, this was evidence of something far more profound. Space itself was expanding, stretching like the surface of a balloon being inflated, carrying galaxies along with it, like dots painted on that balloon's surface. From any galaxy's perspective, all the other galaxies would appear to be moving away, with more distant ones receding faster. There was no center to this expansion. It was happening everywhere at once. This discovery, published in 1929, gave tremendous weight to Lemaitre's idea. If the universe was expanding now, then indeed, it must have been smaller in the past, much smaller. Working backward through time, all those galaxies rushing apart would come together, space would contract, and eventually you'd reach a point where everything was compressed into an incredibly small, dense, hot state. The implications were staggering. The universe had a beginning. It hadn't always existed in its current form. There was a moment, a specific point in time roughly 14 billion years ago, when everything started. But not everyone was convinced. The idea seemed almost too fantastic, too much like religious creation mythology dressed up in scientific language. Some scientists, including the renowned British astronomer Fred Hoyle, preferred what was called the steady-state theory. This theory suggested that the universe had no beginning and no end, that it had always existed and always would exist in much the same form. Yes, the universe was expanding, but as it expanded, new matter was continuously being created in the spaces between galaxies, keeping the overall density constant. The universe, in this view, was eternal and essentially unchanging on the larger scales, always looking roughly the same at any point in time. The steady-state theory had a certain philosophical appeal. It avoided the awkward question of what came before the beginning. It eliminated the need for a creation event. The universe simply was, and always had been, and always would be. It was elegant in its own way. Ironically, it was Hoyle himself who gave Lemaitre's theory its famous name. During a BBC radio broadcast in March of 1949, Hoyle was trying to explain the difference between his steady-state theory and Lemaitre's idea of an explosive beginning. He referred to Lemaitre's concept somewhat dismissively as this Big Bang idea. The name was meant to emphasize how ridiculous the notion seemed to him, this idea that everything exploded out of a single point. But the name stuck. And though it was meant as a slight, though Hoyle later claimed he didn't intend it to be pejorative, the Big Bang became the most famous scientific theory of our time. Sometimes the best names come from the most unexpected places. For a while, both theories had their supporters. The scientific community was divided. Arguments were made on both sides. The steady-state theory was philosophically attractive and avoided some conceptual difficulties. But the Big Bang had the expanding universe on its side, and it made specific, testable predictions about what we should observe if it were true. Science, ultimately, is decided not by philosophy or by what seems aesthetically pleasing, but by evidence. And in 1964, that evidence arrived in a most unexpected way. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in New Jersey with a large, horn-shaped antenna that had originally been built for satellite communications. They were using this antenna to study radio emissions from our Milky Way galaxy, trying to create detailed maps of these emissions. But they encountered a problem. No matter how carefully they calibrated their instrument, no matter how many potential sources of interference they eliminated, they kept picking up a strange, persistent hiss of static. This noise wasn't coming from any particular direction in the sky. It wasn't stronger during the day when the sun was up. It didn't correlate with the plane of the Milky Way. It was everywhere, uniform across the entire sky, a steady, unchanging signal. They checked everything. They wondered if it might be radio interference from New York City. They pointed the antenna directly at the city. No, that wasn't it. They wondered if it might be coming from the instrument itself. They checked and rechecked their electronics. Everything was functioning properly. Then they noticed that a pair of pigeons had been nesting inside the horn-shaped antenna. Birds can be messy creatures, and these pigeons had left behind what Penzias and Wilson delicately referred to as a white dielectric material. Less delicately, it was pigeon droppings, quite a lot of them, crusted all over the inside of the antenna. Perhaps that was the source of the noise. They trapped the pigeons, relocated them some distance away. The pigeons flew back. They trapped them again, relocated them again. This time the pigeons stayed away. Then Penzias and Wilson spent considerable time cleaning the antenna, scrubbing away every trace of the white dielectric material. It was painstaking work, but they were determined to eliminate this source of potential interference. They turned the antenna back on. The noise was still there. It had nothing to do with pigeons or their droppings. It was a real signal, coming from space, from every direction equally. But what was it? Penzias and Wilson were baffled. They had accidentally stumbled upon something extraordinary, though they didn't yet realize its significance. Meanwhile, just 60 kilometers down the road at Princeton University, a group of physicists led by Robert Dicke had been developing theoretical predictions about the early universe. They were thinking about what the universe would have been like in its infancy, in the immediate aftermath of the Big Bang, if such an event had actually occurred. They realized that in its earliest moments, the universe would have been incredibly hot, filled with intense radiation. As the universe expanded and cooled, this radiation would cool too, its wavelengths stretching along with the expansion of space itself. By now, billions of years later, this radiation should have cooled to just a few degrees above absolute zero, that coldest of all possible temperatures. It should be detectable as faint microwave radiation, coming uniformly from all directions in the sky. In fact, Jim Peebles, a young physicist working with Dick, had just written a paper predicting that this cosmic background radiation should exist and should be observable with current technology. And Dick's team was actually building an instrument to search for it, an antenna they would mount on the roof of their building at Princeton. They were racing to be the first to detect this crucial evidence for the Big Bang theory. But they were too late. When news of Penzias and Wilson's mysterious signal reached Princeton, likely through a mutual friend, Dick immediately understood what it meant. He hung up the phone after learning about the discovery and turned to his colleagues. The story goes that he said, somewhat ruefully, "Boys, we've been scooped." That persistent hiss Penzias and Wilson had been trying to eliminate wasn't interference. It wasn't noise. It was the signal they'd been looking for. It was the echo of creation itself. Penzias called Dick to discuss what they'd found. Dick and his team drove up to Bell Labs to examine the antenna and listen to the signal. They confirmed it. This was cosmic microwave background radiation, the afterglow of the Big Bang, stretched and cooled by nearly 14 billion years of cosmic expansion, but still detectable, still carrying information about the early universe. The temperature of this radiation was measured at about 3 degrees Kelvin, 3 degrees above absolute zero, remarkably close to what the theory had predicted. This discovery was revolutionary. Here was direct evidence, observable proof that the universe had indeed begun in a hot, dense state and had been expanding and cooling ever since. The cosmic microwave background wasn't just a prediction that happened to be confirmed. It was a fossil, a relic from the earliest age of the cosmos, preserved in the very fabric of space. You could think of it as the oldest light in the universe, released when the cosmos was just 380,000 years old, and traveling through space ever since. The cosmic microwave background became one of the most important discoveries in the history of science. It settled the debate between the Big Bang and the steady-state theory decisively in favor of the Big Bang. The steady-state theory simply couldn't explain this uniform background of ancient radiation. Penzias and Wilson would later receive the Nobel Prize in Physics for their accidental but momentous discovery. And the Big Bang theory moved from controversial hypothesis to accepted scientific fact, the cornerstone of modern cosmology. So now we know the universe had a beginning. We have evidence for it, clear observational proof. But what was that beginning like? What happened in those first moments? What was the universe like when it was young? This is where our story gets truly extraordinary, where we venture into realms that stretch our imagination to its very limits, where we must think about conditions so extreme that they challenge our very conception of reality. The Big Bang was not an explosion in space, and this is worth emphasizing because it's such a common misconception. When we hear the word bang, we naturally think of something exploding, of a bomb going off perhaps, sending debris flying outward into the surrounding space. But the Big Bang wasn't like that at all. There was no pre-existing void into which the universe exploded. There was no space surrounding the initial point, no container that held it. Space itself was born in the Big Bang. Time itself was born in the Big Bang. Before the Big Bang, if we can even use the word before when talking about a moment when time didn't exist, there was nothing. No space, no time, no matter, no energy. Nothing. This is admittedly hard to grasp. Our minds are wired to think in terms of cause and effect, of things happening in time and occupying space. We expect everything to have a before and an after, to exist somewhere. But at the Big Bang, time and space came into existence together. They are part of the universe, not something the universe exists within. The universe didn't expand into something. It simply expanded, creating space as it went, bringing into existence the very fabric of reality itself. Now, let's imagine we could somehow rewind the cosmic clock, watching the universe contract, growing smaller and denser and hotter as we go back in time. We'd see the galaxies rushing together, converging from all directions. We'd see stars dissolving, breaking down into their component elements as temperatures climbed higher. We'd see atoms torn apart into electrons and nuclei. We'd see atomic nuclei themselves disintegrating into protons and neutrons. The temperature would climb higher and higher, the density greater and greater. At about 13.8 billion years ago, give or take a few tens of millions of years, we would reach a point where the entire observable universe, everything we can see today, stretching tens of billions of light years in every direction, would be compressed into a region smaller than an atom, smaller than a proton, smaller than anything we can directly observe. The density would approach infinity. The temperature would approach infinity. The very concepts of space and time would start to break down. The laws of physics as we understand them, the equations that describe how things behave, would stop making sense. This is what physicists call a singularity, a point where our current mathematical descriptions of reality simply fail, where the equations spit out infinities and nonsense. We cannot know what happened at the exact moment of the singularity, at that point of infinite density and infinite temperature. Our physics, our mathematics, all the tools we've developed to understand the universe, they all break down there. General relativity, which describes gravity and the large-scale structure of space-time, says there should be a singularity. But quantum mechanics, which describes the behavior of particles at the smallest scales, suggests that there can be no true infinities in nature, that something else must happen at those extreme conditions. We need a theory of quantum gravity, a way to combine general relativity and quantum mechanics, to truly understand what happened at that very first instant. And despite decades of work, despite brilliant minds working on the problem, we don't yet have such a theory. But we can describe what happened just after, in the first fractions of a second. And what a fraction of a second it was. Our understanding is pretty solid from about 10 to the minus 43 seconds onward. That's a decimal point, followed by 42 zeros, then a 1. That's the Planck time, the smallest meaningful unit of time, and it marks roughly where our current physics can begin to make sense of things. The universe, in those earliest moments, was a seething, roiling cauldron of pure energy. It was far too hot for matter as we know it to exist. There were no atoms, no protons, no neutrons, not even quarks at first. Just energy and radiation in its most fundamental form. A soup of elementary particles and their antimatter counterparts, appearing and disappearing in the chaos. Photons of incredible energy, and the quantum fields that pervade space. The temperature was unimaginably high, on the order of 10 to the 32 degrees Kelvin. To put this in any kind of perspective, the center of our sun, where nuclear fusion occurs continuously, has a temperature of about 15 million degrees Celsius. The early universe was quintillions of times hotter than that. It's a temperature that's hard even to conceptualize, so far beyond anything in our everyday experience. In the very first fraction of a second after the Big Bang, according to our best current theories, something remarkable is believed to have happened. Something so dramatic that it shaped the entire future of the cosmos, that determined the very structure and nature of the universe we inhabit today. This is the period known as cosmic inflation, and it's one of the most important and fascinating ideas in modern cosmology. It's also, it must be said, still somewhat speculative, still being tested and refined, but the evidence for it grows stronger with each new observation. The story of cosmic inflation begins with a series of puzzles, problems that cosmologists noticed with the standard Big Bang model. The Big Bang theory was successful in many ways. It explained the expansion of the universe. It explained why space is filled with microwave radiation. It would later make successful predictions about the abundance of light elements like hydrogen and helium. But there were a few nagging problems, features of the universe that seemed to require incredibly precise, almost impossibly fine-tuned initial conditions. And scientists don't like fine-tuning. When a theory requires you to dial in numbers to ridiculous precision, with no explanation for why those numbers have the values they do, it suggests something is missing from your understanding. One problem was called the horizon problem. When we observe the cosmic microwave background radiation, that faint afterglow of the Big Bang, we see something remarkable. The temperature is almost exactly the same in every direction we look. If we point our radio telescope at one patch of sky and measure the temperature of the background radiation, then point it at a completely different patch on the opposite side of the sky, the temperatures match to within 1 part in 100,000. This uniformity is extraordinary. It tells us that different regions of the early universe, regions that are now on opposite sides of the observable cosmos, tens of billions of light years apart, somehow started with almost exactly the same temperature and density. But here's the puzzle. According to the standard Big Bang model, these regions would have been too far apart to have ever been in contact with each other, even at the very beginning. Light, traveling at the cosmic speed limit, at the fastest speed at which information can be transmitted through space, wouldn't have had time since the Big Bang to travel between these distant regions. They couldn't have communicated. They couldn't have influenced each other. So how did they know to have the same temperature? How did they reach thermal equilibrium? That state where everything has come to the same temperature through the exchange of heat. It's as if you had two isolated rooms on opposite sides of the Earth, rooms that had never been connected, where no one from one room had ever visited the other room or communicated with anyone from the other room in any way. And yet, when you measure the temperature in both rooms, you find they're exactly the same, down to the thousandth of a degree. That would be bizarre. That would demand an explanation. You'd suspect that somehow, at some point, those rooms had been connected, had been able to influence each other. The horizon problem in cosmology was similar. These distant regions of the universe appeared to be in thermal equilibrium, despite never having been in causal contact. Another problem was the flatness problem, and this one involves the geometry of space itself. In Einstein's general relativity, space is not just an empty stage where things happen. Space itself is a dynamic entity. It can be curved by the presence of matter and energy. The density of matter and energy in the universe determines the curvature of space. If there's enough density, space curves back on itself like the surface of a sphere. If you traveled far enough in what you thought was a straight line, you'd eventually come back to where you started. Cosmologists call this a closed universe. If the density is too low, space curves outward like a saddle, and it's infinite in extent. This is called an open universe. And if the density is just right, at a precise critical value, space is flat, like a sheet of paper, extending infinitely in all directions. This is called a flat universe. Now, observations show that our universe is remarkably flat. It's not perfectly flat. No measurement is perfect, but it's flat to within a percent or so of that critical density. This seems unremarkable until you realize what it implies about the early universe. The thing about the flatness of space is that it's unstable. If the universe starts out even slightly curved, that curvature grows over time. A universe that's 1% too dense in its early moments will collapse into a big crunch in relatively short order. A universe that's 1% too sparse will become dramatically open, with space curving away, density plummeting. The fact that our universe is still so close to flat after nearly 14 billion years of expansion means that in its very earliest moments, it must have been extraordinarily, absurdly close to the critical density. How close? Well, at 1 second after the Big Bang, for the universe to still be anywhere near flat today, the density would have had to equal the critical density to within 1 part in 10 to the 15th. That's 1 part in 1 quadrillion. It's like balancing a pencil on its point, except you'd need to balance it not for a second, but for billions of years, keeping it from tipping in either direction. This kind of fine-tuning cries out for an explanation. Why should the initial density of the universe be set to such exquisite precision? What mechanism could arrange that? There were other problems too. Grand unified theories of particle physics, attempts to understand how the fundamental forces of nature relate to each other, predicted that certain exotic particles should have been created in the early universe. These included magnetic monopoles, hypothetical particles that would be like isolated north or south magnetic poles, not part of a pair as all real magnets are. If these monopoles were created in the very early universe, they should be common today. We should be tripping over them. But we've never found even one. Where did they all go? In 1980, a young physicist named Alan Guth was pondering these problems. Guth had trained as a particle physicist, not a cosmologist. He was working at Cornell University as a postdoctoral researcher, relatively early in his career, attending lectures and seminars on various topics in physics. In the fall of 1978, he attended a series of talks by the distinguished physicist Robert Dicke. Yes, the same Dicke who had been involved in understanding the cosmic microwave background. Dicke was lecturing about cosmology, about the Big Bang, and he explained the flatness problem in detail. This was Guth's first real exposure to the problem, and it captured his imagination. Over the following months, Guth thought about these cosmological puzzles. He thought about the early universe, about the extreme conditions that prevailed then, about particle physics and quantum fields and phase transitions. And in December of 1979, while working on something else entirely, a problem involving magnetic monopoles, he had a sudden insight. What if, in the very first moments after the Big Bang, the universe underwent a period of exponentially rapid expansion? What if, for a brief instant lasting only a tiny, almost incomprehensibly tiny fraction of a second, space expanded faster than the speed of light? Now, this might sound like it violates Einstein's relativity, which says nothing can move faster than light. But it doesn't. The speed limit applies to things moving through space, to matter and energy and information. But space itself can expand at any rate it likes. There's no law against the expansion of space exceeding the speed of light. In fact, even today, in our gently expanding universe, there are galaxies so distant that they're receding from us faster than light because of the expansion of space between us and them. We can't see beyond a certain distance, not because light from farther away hasn't had time to reach us, but because space is expanding so fast out there that light can never bridge the gap. So Guth imagined this period of incredibly rapid expansion in the early universe. And he realized that this could solve the horizon problem. Here's how. Imagine a small region of space in the earliest moments of the universe. A region tiny enough that light could cross it many times. A region small enough that different parts of it could be in thermal contact, could exchange heat, and reach the same temperature. Now imagine this region suddenly begins to inflate, to grow exponentially, doubling in size again and again in the tiniest fraction of time. Every 10 to the minus 35 seconds or so, it doubles, and it keeps doubling. In less time than it takes to even think about it, this once tiny patch, small enough to fit inside an atom, grows to become larger than our entire observable universe today, larger than tens of billions of light years across. All the regions we see when we look at the cosmic microwave background, all those distant patches of sky that seem too far apart to have ever influenced each other, they all started out in that tiny, causally connected region before inflation blew them apart. They were close together once, close enough to reach the same temperature, to smooth out any differences. Then inflation took them and scattered them across cosmic distances. That's why they still have the same temperature today. They inherited it from their common origin. The horizon problem solved. And the flatness problem? Inflation would stretch space so dramatically, so violently, that any initial curvature it might have had would be smoothed out completely. Imagine a balloon with a wrinkled surface. Now blow it up, and keep blowing. As it expands, the wrinkles flatten out. By the time the balloon is enormous, its surface appears perfectly smooth and flat to any observer on that surface. That's what inflation does to the universe. It doesn't matter what the initial geometry was. It doesn't matter what the initial curvature of space might have been. Inflate it enough, and it will become flat. No fine-tuning required. The universe is flat because inflation made it flat. Problem solved. And the magnetic monopoles? If they were created before inflation, then inflation would dilute them, spreading them across such vast distances that we'd never expect to find one in our observable universe. They'd still exist, but they'd be so sparse, scattered so thinly, that encountering one would be astronomically unlikely. Problem solved. Guth's idea was elegant and powerful. It solved multiple problems at once with a single mechanism. He published his paper in 1981, and it quickly attracted attention in the physics community. Other physicists, including Andrei Lind in the Soviet Union working independently, and Andreas Albrecht and Paul Steinhardt in the United States, saw the same problems and came up with similar solutions, refining and improving the concept. Lind, in particular, developed what's called new inflation and chaotic inflation, versions of the theory that worked better than Guth's original proposal, and are closer to what cosmologists work with today. The theory of cosmic inflation became a cornerstone of modern cosmology. It's not without its critics, and it's still being tested and refined, but it makes specific predictions that can be checked against observations, and so far, it's passing those tests remarkably well. But let's think about the scale of what we're describing here. How fast was this inflation? How much did the universe grow? The numbers are almost impossible to grasp. In a period lasting perhaps 10 to the minus 32 seconds, that's a decimal point followed by 31 zeros and then a 1. A time interval so brief that a billion of these intervals would fit into a single second. The universe expanded by a factor of at least 10 to the power of 26. That's a 1 followed by 26 zeros. To put that in perspective, if you started with something the size of a proton, one of the particles in an atomic nucleus, and inflated it by that factor, you'd end up with something about 10 billion kilometers across, larger than the orbit of Neptune, the outermost major planet in our solar system. And that's a conservative estimate. Some models of inflation have the universe expanding by even larger factors, perhaps 10 to the power of 78 or more. This inflation was driven by something physicists call the inflaton field. Now, a field in physics is a fundamental entity that exists throughout space. You're familiar with some fields already. The electromagnetic field, for instance, is what gives rise to electric and magnetic forces. The Higgs field is what gives particles their mass. These fields pervade space, and their excitations, their vibrations, manifest as particles. The photon, the particle of light, is an excitation of the electromagnetic field. The Higgs boson, discovered at the Large Hadron Collider in 2012, is an excitation of the Higgs field. The inflaton field is similar, a quantum field that filled space in the very early universe. Under normal conditions, this field sits at its minimum energy state, its ground state, contributing nothing. But in the extreme conditions immediately after the Big Bang, the inflaton field could get stuck in what's called a false vacuum state, a higher energy state that's stable for a while. And while it was in this false vacuum state, it created a kind of repulsive gravity, an anti-gravity if you will, though that's not quite the right term. This repulsive force drove the exponential expansion, pushing space apart faster and faster. Eventually, the inflaton field transitioned to its true minimum energy state. It rolled down to the bottom of its potential energy curve, to use the technical language. When it did this, all that energy that had been locked up in the field was released. It converted into particles and radiation, into quarks and electrons and photons, and all the other constituents of the hot early universe. This moment, when inflation ended and the energy was released, is sometimes called reheating. The universe was already hot, mind you, but the end of inflation released a flood of particles and energy that would go on to form everything we see today. Inflation also explains something else, something rather wonderful and profound. The universe we observe today isn't perfectly smooth. It's not uniform. There are galaxies clustered together in groups and clusters and superclusters. There are vast voids, regions hundreds of millions of light-years across, that contain very few galaxies. There are filaments and sheets of matter, structures on the largest scales. Where did all this structure come from? How did the universe go from a nearly smooth, uniform state to the richly textured cosmos we see today? According to inflation theory, these structures began as quantum fluctuations, tiny random variations in the inflaton field itself. At the quantum level, nothing is perfectly smooth. The Heisenberg uncertainty principle, a fundamental feature of quantum mechanics, guarantees that there are always small fluctuations, tiny random variations in the value of any field. In ordinary circumstances, these quantum fluctuations are microscopic, far too small to notice. But during inflation, something remarkable happened. These quantum fluctuations were stretched. As space expanded exponentially, these tiny variations were blown up to cosmic proportions. A quantum fluctuation that started smaller than an atom became larger than a galaxy, then larger than a galaxy cluster, then larger than a supercluster. When inflation ended, these stretched quantum fluctuations became variations in the density of matter and energy. Some regions were slightly denser than average, some were slightly less dense. And these density variations became the seeds from which all structure in the universe would later grow. The denser regions had slightly more gravity. They attracted nearby matter. Over time, over millions and billions of years, these small density enhancements grew. Matter collected in the denser regions. Stars formed. Galaxies formed. Galaxy clusters formed. The cosmic web of structure we see today, with its filaments and voids, grew from those quantum seeds planted during inflation. This is one of the most remarkable ideas in all of science. The galaxies we see today, including our own Milky Way, the solar system, the Earth, you, me, all of it traces back to quantum fluctuations that occurred when the universe was unimaginably small and young. Fluctuations that were stretched to cosmic proportions by inflation. Everything large came from something impossibly tiny. The quantum and the cosmic are connected in the most intimate way. We can actually see these primordial fluctuations. When we observe the cosmic microwave background radiation with sufficient precision, we see tiny temperature variations, hot spots and cold spots. These variations are incredibly small, about 1 part in 100,000, but they're there. And they match the pattern predicted by inflation. The hot spots correspond to regions that were slightly denser in the early universe, regions where gravitational potential wells created a slight blue shift in the radiation. The cold spots correspond to less dense regions, and the statistical properties of these hot and cold spots, their distribution, their sizes, all of it matches what inflation predicts. It's a stunning confirmation of the theory. After inflation ended, the universe continued to evolve. It was still unimaginably hot and dense, but now it was filled with particles and radiation, with quarks and electrons and photons and neutrinos and their antimatter counterparts, all swimming in a primordial soup. The temperature was still on the order of 10 to the 27 or 10 to the 28 degrees, cooling as the universe expanded, but still incomprehensibly hot. At these extreme temperatures, the fundamental forces of nature, the forces that govern how particles interact, were still partially unified. Today, we know of 4 fundamental forces: gravity, which holds planets in orbit around stars and galaxies together, the force described by Einstein's general relativity; electromagnetism, which gives us light and radio waves and holds atoms together, the force described by quantum electrodynamics; the strong nuclear force, which binds quarks together into protons and neutrons and holds atomic nuclei together despite the electromagnetic repulsion of protons; and the weak nuclear force, which governs certain forms of radioactive process. But in the early universe, these forces weren't all distinct. At high enough temperatures, the electromagnetic force and the weak force are unified into a single electroweak force. At still higher temperatures, the strong force might join in, creating a grand unified force. And at the very highest temperatures, perhaps even gravity joins the unification, though this is speculative because we don't have a working theory of quantum gravity yet. As the universe expanded and cooled, these forces separated, took on their modern forms through processes called symmetry breaking. First, gravity separated. Then, at around 10 to the minus 35 seconds after the Big Bang, give or take, the strong force separated from the electroweak force. This is likely when inflation occurred. And then later, at around 10 to the minus 11 seconds, at a temperature of about 10 to the 15 degrees, the electroweak force split into the electromagnetic and weak forces as we know them today. This happened through something called the Higgs mechanism, involving the Higgs field, and it's when particles acquired their masses. In these early moments, the universe was also a soup of quarks and gluons. Quarks are the building blocks of protons and neutrons. Gluons are the particles that carry the strong nuclear force, binding quarks together. But at the extreme temperatures of the first microsecond after the Big Bang, quarks couldn't yet form stable bound states. The temperature was too high, the energy too great. Any time a few quarks came together to try to form a proton or neutron, they'd immediately be blasted apart again by the intense radiation. The universe was a quark-gluon plasma, a state of matter so extreme that we've only been able to recreate it for the briefest instance in particle colliders like the Large Hadron Collider and the relativistic Heavy Ion Collider. But as the universe expanded, it cooled. This is an inexorable consequence of expansion. When you compress a gas, it heats up. When you allow a gas to expand, it cools down. The same principle applies to the universe. As space expanded, carrying matter and radiation along with it, the energy became more dilute. The temperature dropped. And at about 1 microsecond after the Big Bang, about 1/1,000,000th of a second, the temperature had dropped to around 10 to the 13 degrees Kelvin. This was just low enough for quarks to finally stick together permanently. Protons and neutrons formed and became stable. This transition, from a quark-gluon plasma to a universe filled with stable protons and neutrons, is called the QCD transition, or quark confinement, named after quantum chromodynamics, the theory of the strong force. It was one of the great phase transitions in cosmic history, like water freezing into ice or steam condensing into liquid, except on a cosmic scale and at unimaginable temperatures. Now the universe contained protons and neutrons, the building blocks of atomic nuclei, though they were still far too hot and energetic to bind together into actual nuclei. That would come later. At this point, the ratio of neutrons to protons was about 1:1. They were being continuously interconverted through weak interactions. A neutron could absorb a positron and turn into a proton. A proton could absorb an electron and turn into a neutron. Back and forth, maintaining an equilibrium. But neutrons are slightly more massive than protons. It takes a tiny bit more energy to make a neutron than a proton. So as the universe continued to cool, as the available energy decreased, the equilibrium shifted. It became slightly easier to make protons than neutrons. The ratio began to favor protons. At about 1 second after the Big Bang, the temperature had dropped to around 10 billion degrees Kelvin. This is still incredibly hot by any ordinary standard, hotter than the core of the most massive stars, but it's cool by comparison to what came before. At this temperature, neutrinos, those ghostly particles that barely interact with anything, decoupled from the rest of matter. They stopped interacting. They began traveling freely through space. They're still out there today, these primordial neutrinos, forming what's called the cosmic neutrino background, analogous to the cosmic microwave background, but even more ancient and even more diffuse. We've never directly detected these relic neutrinos, and we probably won't for a long time, but we're quite confident they exist. Also around this time, the interconversion between neutrons and protons essentially stopped. The weak interactions that were mediating this conversion became too slow to keep up with the expansion of the universe. The ratio of neutrons to protons froze out at about 1 neutron for every 6 or 7 protons. This ratio would become crucial for what happened next. Between about 10 seconds and 20 minutes after the Big Bang, the universe underwent another crucial transformation. This is the epoch known as Big Bang nucleosynthesis, primordial nucleosynthesis, the forging of the first atomic nuclei. It's one of the great triumphs of the Big Bang theory, because it makes precise, quantitative predictions about the abundances of light elements that we can test against observations. The process began as soon as the temperature dropped low enough for nuclear fusion to occur without the products being immediately torn apart again. But there was a bottleneck. To build up heavy nuclei, you need to start with deuterium, heavy hydrogen, which consists of one proton and one neutron bound together. Deuterium is the crucial first step. But deuterium is fragile. Its binding energy is low. At temperatures above about 1 billion degrees, there's enough energetic radiation around that any deuterium nucleus that forms is quickly torn apart again by a high-energy photon smashing into it. This is the deuterium bottleneck. So for the first few minutes, even though nuclear fusion reactions could in principle occur, they were stymied because deuterium couldn't survive long enough to participate in subsequent reactions. The universe had to cool below that billion-degree threshold. Once it did, around 3 minutes after the Big Bang, the bottleneck cleared. Deuterium could finally survive, and once it did, fusion proceeded rapidly. Neutrons and protons combined to form deuterium. Deuterium nuclei captured additional neutrons, forming tritium, radioactive heavy hydrogen with 2 neutrons and 1 proton. Or they captured additional protons, forming helium-3 with 2 protons and 1 neutron. And these, in turn, could fuse together to form helium-4 with 2 protons and 2 neutrons, the stable and very tightly bound nucleus of ordinary helium. Almost all of the free neutrons that existed at this point ended up bound into helium-4. Remember, there was about 1 neutron for every 6 or 7 protons. These neutrons, being unstable when free, needed to find a home, and helium-4 provided that home. By the time Big Bang nucleosynthesis ended, about 20 minutes after the Big Bang, roughly 25% of the mass of ordinary matter in the universe was helium, with most of the rest being hydrogen. Tiny amounts of deuterium, helium-3, lithium and beryllium were also created, typically less than 1 part per million for lithium and beryllium, and somewhat more for deuterium and helium-3. This prediction, that about a quarter of ordinary matter should be helium, is remarkably robust. It depends primarily on that frozen-out ratio of neutrons to protons, and on fundamental physics that we understand well. And when we go out and measure the helium abundance in the universe today, when we look at the oldest stars, at gas clouds in distant galaxies, at regions that have been least affected by subsequent stellar evolution, we find that about 25% of the mass is helium. The match is extraordinary. It's one of the strongest pieces of evidence we have that the Big Bang really occurred and that we understand the nuclear physics that governed those early minutes. Stars can make helium too, of course. Our Sun is fusing hydrogen into helium in its core right now. But stars can't make enough helium to account for what we observe. The production rate is too low. The only way to produce as much helium as we see is if a significant amount was created in the Big Bang itself. Big Bang nucleosynthesis couldn't produce elements heavier than lithium and beryllium in any significant amounts. There's a gap in the nuclear stability chart. An absence of stable nuclei with 5 nucleons, with mass number 5, and with 8 nucleons. You can't easily jump these gaps through fusion in the early universe. Fusion of helium-4 with a proton or neutron gives you mass 5, but those nuclei are unstable and quickly break apart. Fusion of 2 helium-4 nuclei gives you mass 8, beryllium-8. But that's also unstable, so fusion stalls out. It can't proceed to make carbon and heavier elements. This means that all the heavier elements, the carbon in our bodies, the nitrogen in the air, the oxygen we breathe, the calcium in our bones, the iron in our world and our cells, all of these were created later, much later, in the cores of stars through stellar nucleosynthesis and in supernova explosions. We are, as Carl Sagan so eloquently put it, made of star stuff. Our bodies contain atoms that were forged in the hearts of distant stars that lived and perished billions of years ago, scattering their enriched material back into space to be incorporated into new stars, new planets, and eventually, us. But the hydrogen and helium that make up most of the universe, those came from the Big Bang itself. They are primordial, forged in the first minutes of cosmic history. After Big Bang nucleosynthesis, the universe continued to expand and cool. But for hundreds of thousands of years, it remained opaque. The reason is that the universe was still too hot for atoms to form. We had nuclei, protons, and helium nuclei, and we had electrons, but they couldn't stay together. The temperature was still high enough that any electron trying to settle into an orbit around a nucleus would quickly be knocked free again by an energetic photon or by collisions with other particles. So the universe was filled with free electrons, electrically charged particles zipping around at high speeds. And free electrons scatter light very efficiently. Any photon trying to travel through space would quickly encounter a free electron and be knocked in a random direction. Then it would encounter another electron and be scattered again. Light couldn't travel far. It couldn't move in straight lines through space. It was trapped, bouncing endlessly from electron to electron. The universe was opaque, like being inside a thick fog. Imagine trying to see through a cloud, a dense white cloud like those you sometimes fly through in an aeroplane. You can't see far because the tiny water droplets in the cloud scatter light. Every photon from your flashlight bounces off a droplet, then another, diffusing in all directions, and very little light makes it through. The early universe was like that, except instead of water droplets, it was free electrons doing the scattering. But as the universe expanded, it continued to cool. And at about 380,000 years after the Big Bang, when the universe was less than 1/10,000th of its current age, the temperature dropped to about 3,000 degrees Kelvin. This is still hot enough to glow white hot if you could see it, about half the temperature of the surface of our sun, but it was cool enough for a crucial transition to occur. Electrons could finally be captured by atomic nuclei. Hydrogen atoms formed, with electrons settling into orbits around protons. Helium atoms formed, with electrons orbiting helium nuclei. This epoch is called recombination, though that's a bit of a misnomer, since it was the first time atoms had ever formed, not a recombining. With electrons now bound into atoms, there weren't enough free electrons left to scatter light. Suddenly, the universe became transparent. Photons could travel freely through space without being scattered. The cosmic fog cleared. It's as if you were inside that dense cloud, and suddenly all the water droplets evaporated at once, and you could see clearly for the first time. This moment, this transition from an opaque plasma to a transparent gas of neutral atoms, is one of the most important events in cosmic history. All those photons that had been bouncing around, trapped in the plasma, were suddenly free. They streamed off into space, and they've been traveling ever since, for over 13 billion years. And we can see them today. This is the cosmic microwave background radiation that Penzias and Wilson discovered. When the light was released, it was in the visible spectrum, glowing orange-white like heated metal. But as it traveled through space, it was stretched by the expansion of the universe. The wavelengths grew longer and longer. What was once visible light became infrared, then far infrared, then microwave radiation. Today, these photons have wavelengths of about a millimeter, corresponding to a temperature of 2.73 degrees above absolute zero. We can't see this radiation with our eyes, but we can detect it with sensitive radio receivers. It fills all of space. It comes from every direction equally. It's the oldest light in the universe, a snapshot of what the cosmos looked like when it was just 380,000 years old. The cosmic microwave background is profoundly important to cosmology. It's our window into the early universe. Before recombination, the universe was opaque, so we can't see farther back using electromagnetic radiation. The cosmic microwave background is our horizon, the edge of what light can reveal to us. But it contains a wealth of information. Those tiny temperature variations we mentioned, the hot and cold spots, they tell us about the density variations in the early universe that would later grow into galaxies. The overall spectrum of the radiation, how its intensity varies with wavelength, matches a perfect blackbody curve to exquisite precision, confirming that it comes from a hot thermal source. And subtle patterns in the polarization of the radiation may yet reveal evidence of gravitational waves from the inflationary epoch. After recombination, the universe entered what cosmologists call the Dark Ages. Not because anything sinister was happening, but simply because there were no stars yet. The universe consisted of a vast expanse of hydrogen and helium gas, now in the form of neutral atoms, with only the faint glow of the cooling cosmic microwave background to illuminate it. It was dark. It was cold, relatively speaking, just a few tens of degrees above absolute zero. The gas was mostly uniform, but with those slight variations in density left over from inflation, imprinted as patterns in the cosmic microwave background. And for the next few 100 million years, not much happened. The universe expanded, the gas cooled. Gravity slowly, patiently did its work. Those slightly denser regions began to attract nearby matter. Where there was more mass, there was more gravity, and the gravity pulled in even more mass, making the region denser still. This is called gravitational instability. Any small density enhancement tends to grow over time. The rich get richer. Dense regions become denser, voids become emptier. Over millions of years, clouds of gas began to collapse under their own weight. As they collapsed, they heated up. This might seem paradoxical. How does something get hotter as it expands and cools? But remember, we're talking about gravitational collapse here, not expansion. When you pull something together under gravity, when you compress it, it heats up. Gravitational potential energy is converted into kinetic energy, the random motion of atoms, which we perceive as heat. Deep in the centers of these collapsing clouds, temperatures began to climb. 10,000 degrees, 100,000 degrees, 1,000,000 degrees, 10 million degrees. And finally, at around 10 million degrees, nuclear fusion ignited. Hydrogen nuclei began to fuse into helium, releasing energy. The first stars were born. This moment, perhaps 200 million years after the Big Bang, possibly as early as 100 million years, or as late as 400 million years, we're not entirely sure, marked the end of the cosmic dark ages. The universe lit up again, not with the uniform glow of the cosmic microwave background, but with the light of countless individual stars scattered across space. This epoch is called the cosmic dawn, and it's one of the frontiers of current observational cosmology. Telescopes like the James Webb Space Telescope are designed to peer back to this era, to see the first galaxies forming, to watch the universe emerging from darkness into light. These first stars were not like the stars we see in the sky today. They were different, unusual. made of material that had never been through a star before. Remember, Big Bang nucleosynthesis only produced hydrogen and helium, with tiny traces of lithium and beryllium. There were virtually no heavier elements, no carbon, no oxygen, no nitrogen, no iron. Astronomers have a technical term for elements heavier than helium. They call them metals, even though chemically most of them aren't what we'd call metals. It's just a convenient shorthand. And these first stars had essentially zero metallicity. They're called population 3 stars, the third and oldest population. We've never actually observed a population 3 star directly. They all passed on long ago, their lives measured in mere millions of years. But we can infer what they must have been like from theory and from indirect evidence. Without heavier elements, without metals, gas clouds can't cool as efficiently. Carbon and oxygen and other elements are very good at radiating away energy, at cooling gas. But without them, the clouds stay hotter. And hotter gas requires more mass to collapse under its own gravity. As a result, the first stars were likely massive, very massive. Estimates suggest they might have been tens or even hundreds of times more massive than our Sun. Some might have been 1,000 times more massive, truly enormous. And massive stars burn hot and bright. They shine with tremendous luminosity, millions or tens of millions of times brighter than our Sun. They burn through their nuclear fuel at a prodigious rate, and they live fast and pass on young, lasting only a few million years before exhausting their fuel. In their cores, these massive stars fused hydrogen into helium, then helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, silicon into iron, climbing up the periodic table, creating heavier and heavier elements through the process of stellar nucleosynthesis. For the first time in cosmic history, the universe was manufacturing significant amounts of elements beyond helium. And when these stars reached the end of their short lives, when they'd created iron in their cores and could fuse no further because iron fusion doesn't release energy, they collapsed catastrophically. The core collapsed into a neutron star or black hole. The outer layers rebounded in one of the most violent explosions in the universe, a supernova, so bright that for a brief time a single star could outshine an entire galaxy. These explosions scattered the newly formed elements into space, enriching the surrounding gas. And the shock waves from these supernovae could trigger the collapse of nearby gas clouds, sparking the formation of new stars. These next-generation stars, the second generation to form, would contain small amounts of those heavy elements, a metallicity perhaps 1,000th or 1/10,000th of the Sun's. They're called population 2 stars, and we can observe these. The oldest stars in our Milky Way galaxy, ancient stars in globular clusters and the galactic halo, have very low metallicities, suggesting they formed relatively early in cosmic history. They still contain mostly hydrogen and helium, but there's a sprinkling of heavier elements mixed in, elements that could only have come from previous stars. Generation after generation, the cycle continued. Stars formed from gas enriched by previous stars. They lived. They created more heavy elements in their cores. They passed on, some gently, some explosively, returning their material to space. And the next generation of stars formed from gas that was even more enriched. With each cycle, the metallicity of the universe increased. The interstellar medium, the gas between stars, gradually became more and more contaminated, if you want to call it that, with elements heavier than helium. Our Sun is a latecomer to this cosmic story. It formed about 4.6 billion years ago, less than 10 billion years after the Big Bang. By that time, the gas in our region of the Milky Way had been enriched by countless generations of stars. About 2% of the Sun's mass consists of elements heavier than helium. That might not sound like much, but it's far more than the first stars had. And that 2% made all the difference. It allowed planets to form. Rocky planets like Earth require silicon, oxygen, magnesium, iron. Gas giant planets can form more easily when there are solid particles of heavier elements to seed their growth. And of course, life as we know it absolutely requires heavy elements. Carbon, nitrogen, oxygen, phosphorus, and many others. Without the heavy elements forged in the hearts of previous stars, none of us would be here. Every atom of carbon, nitrogen, oxygen, and iron in your body, every bit of calcium in your bones, every trace element, came from stars that existed before our sun was born. They were synthesized in stellar cores, released in supernova explosions, scattered through space, eventually incorporated into the cloud of gas and dust that collapsed to form our solar system. We truly are children of the stars. Our bodies are made of recycled stardust. This isn't poetry or metaphor, it's literal truth. As stars formed, they didn't form in isolation. Gravity was working on larger scales too, organizing the universe, building structure. Stars clustered together into galaxies, vast cities of stars, bound together by their mutual gravitational attraction. Early galaxies were smaller and more numerous than galaxies today. They were irregular, chaotic, still forming, still evolving. Over time, these early galaxies merged, colliding and combining, building up larger galaxies. Galaxies themselves gathered into groups and clusters. A group might contain a few dozen galaxies. A cluster might contain hundreds or thousands. And clusters gathered into superclusters, vast structures hundreds of millions of light years across. And the superclusters outlined filaments and sheets of matter, strands of the cosmic web, separated by enormous voids where few galaxies are found. If you could somehow step back and view the universe on its very largest scales, if you could see the distribution of galaxies across billions of light years, you'd see this cosmic web, this delicate lacework of matter stretched across space. It's beautiful. It's also the result of those initial quantum fluctuations during inflation, amplified by 13 billion years of gravitational evolution. Dense regions attracted more matter and became denser. Voids expelled matter and became emptier. The pattern we see today grew from those primordial seeds. And yet, when we measure how galaxies and clusters move, something doesn't add up. When we observe how fast stars orbit within galaxies, particularly in the outer regions of spiral galaxies, far from the bright central bulge, we find they're moving faster than they should. Much faster. If the only matter present were the stars and gas we can see, the visible matter, then stars in the outer parts of galaxies would be moving relatively slowly. They should follow Kepler's laws, the same laws that govern planetary orbits. The farther you are from the center of mass, the slower you should orbit. But that's not what we observe. We see flat rotation curves. Stars in the outermost observable regions of galaxies are moving just as fast as stars closer in. They shouldn't be able to do this unless there's more mass present than we can see. Additional matter distributed in a large halo around the galaxy, providing the extra gravity needed to keep those fast-moving stars bound to the galaxy. Similar discrepancies appear when we look at galaxy clusters. Galaxies in clusters are moving so fast relative to each other that the cluster shouldn't remain bound. They should fly apart, scattering their galaxies into the wider universe. But they don't. Something is holding them together, providing the gravitational glue. And when we observe gravitational lensing, the bending of light by massive objects as predicted by general relativity, we find that light from distant galaxies is bent more than it should be based on the visible. Matter in foreground galaxy clusters. All of this evidence points to the same conclusion. There's matter out there that we can't see directly. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. It doesn't interact electromagnetically at all, as far as we can tell. But it has mass, and that mass exerts gravity, and that gravity shapes galaxies and clusters. We call it dark matter. We don't know what dark matter is. It's not made of ordinary atoms, of protons and neutrons and electrons. We know this because ordinary matter would have participated in Big Bang nucleosynthesis and would affect the abundances of light elements in ways we don't observe. It must be something else, some new kind of particle or particles that don't interact via the electromagnetic force and interact only very weakly, if at all, via the weak nuclear force. Various hypothetical particles have been proposed. WIMPs, weakly interacting massive particles. Axions, light particles that solve a problem in quantum chromodynamics. Sterile neutrinos, heavier cousins of ordinary neutrinos. Primordial black holes formed in the early universe. Each possibility has proponents and challenges. Experiments deep underground, shielded from cosmic rays, have been searching for dark matter particles for decades, hoping to catch one in the act of colliding with ordinary matter. So far, despite heroic efforts and ever-increasing sensitivity, no confirmed detection has been made. Dark matter remains elusive. What we do know is that dark matter is abundant. Based on our observations of galaxy rotation curves, gravitational lensing, the large-scale structure of the universe, and precise measurements of the cosmic microwave background, we've determined that dark matter makes up about 27% of the total energy and matter content of the universe. That's roughly 5 to 6 times as much as ordinary matter. All the atoms that make up stars and planets and people, and everything we can directly observe. We are, quite literally, the minority component of the cosmos. Most of the matter in the universe is invisible to us, detectable only through its gravitational influence. Because stranger. In the late 1990s, 2 independent teams of astronomers were studying distant supernovae, trying to measure how the expansion of the universe has changed over time. The expectation was that the expansion should be slowing down. All that matter, both ordinary and dark, pulling back through gravity, should be decelerating the expansion. The question was how much? Was there enough matter to eventually stop the expansion and cause the universe to collapse back in on itself in a big crunch? Or would the expansion continue forever, just gradually slowing, asymptotically approaching some final speed? The astronomers used Type 1a supernovae as cosmic distance indicators. These supernovae, which occur when a white dwarf star accumulates too much mass and collapses, have a very consistent peak brightness. Because they're so consistent, because we understand their physics reasonably well, they work like standard candles. If you measure how bright one appears from Earth, you can calculate its distance. And by comparing that distance to the supernova's redshift, which tells you how much the universe has expanded since the light was emitted, you can figure out the expansion history. The teams observed dozens of distant supernovae, explosions so far away that their light had been traveling through space for billions of years. They measured distances and redshifts. They plotted the data, and they got a result that nobody expected. The distant supernovae were farther away than they should be based on their redshifts, and a simple decelerating expansion model. They appeared to be dimmer than expected, as if they were at greater distances. The only way for this to make sense is if the expansion of the universe was not decelerating. It was accelerating. The universe's expansion was speeding up. Something was pushing galaxies apart, counteracting the pull of gravity, and this pushing force was getting stronger. Or perhaps it's better to say, its effect was becoming more noticeable as the universe expanded and matter became more dilute, while this new component remained constant. This was completely unexpected. Nothing in the known laws of physics predicted this. Gravity attracts, matter pulls things together, radiation pulls things together. Even dark matter, mysterious though it is, exerts attractive gravity. So what was pushing things apart? Scientists gave it a name: dark energy. But naming something isn't the same as understanding it, and dark energy remains one of the deepest mysteries in all of physics. The nature of dark energy is still hotly debated. One possibility is that it's related to Einstein's cosmological constant, that mathematical term Einstein added to his equations to keep the universe static. When Hubble discovered the universe was expanding, Einstein reportedly called this his biggest blunder and removed the term. But perhaps Einstein was right after all, just in a way he didn't expect. The cosmological constant would represent a constant energy density of space itself, an intrinsic property of the vacuum, of empty space. As the universe expands and more space comes into existence, more dark energy appears, because it's a property of space. This would naturally lead to accelerating expansion as the universe grows and the energy density of matter becomes more dilute, while the energy density of dark energy stays constant. Another possibility is that dark energy is a new kind of field, a quintessence field, or another exotic entity that fills space and has unusual properties. Unlike matter or radiation, whose energy density decreases as the universe expands, this field could have negative pressure, causing space itself to push outward rather than pull inward. And, unlike the cosmological constant, this field could change over time, making dark energy dynamic rather than constant. Whatever dark energy is, it's dominant. Based on the most recent and precise observations, including studies of the cosmic microwave background by satellites like the Planck spacecraft, observations of supernovae, measurements of the large-scale structure of the universe through galaxy surveys, and gravitational lensing studies, we've determined that dark energy makes up about 68% of the total energy and matter content of the universe. Dark matter accounts for about 27%. Ordinary matter, the stuff we're made of, the stars and planets and gas and dust, everything made of atoms, all of it together comprises less than 5% of the universe. Let that sink in for a moment. Everything we can see, everything we've ever touched or tasted or experienced, everything made of atoms, all the matter that we intuitively think of as the universe, amounts to less than 5% of what actually exists. The rest is dark matter and dark energy, substances we don't understand, that we can't directly observe, but whose effects shape the cosmos on the grandest scales. This realization represents one of the most profound shifts in human understanding since we first looked up at the night sky. For most of history, we assumed that what we could see was essentially all there was. The ancients looked up and saw stars, and they assumed those stars were the universe. Then we discovered that stars are distant suns, and there might be planets around them. Then we learned our sun is one star among billions in the Milky Way galaxy. Then we discovered the Milky Way is one galaxy among countless billions. Each revelation expanded our conception of reality. But the discovery of dark matter and dark energy is different. It's not just that the universe is larger than we thought. It's that the universe contains fundamentally different kinds of stuff than we thought. Stuff that doesn't interact with light or with us in any obvious way. Stuff we can only detect through its gravitational effects. Imagine living your whole life in a house, thinking you understood it completely, every room, every corner. Then one day, you discover that what you thought was the whole house is actually just 5% of it. There are entire wings you never knew existed, rooms you can't see or enter, but whose presence affects how the whole structure behaves, how it settles, how it responds to storms. That's essentially what's happened with our understanding of the universe. We've discovered that the reality we're familiar with, the matter made of atoms, is just a small fraction of what exists. This is one of the most humbling realizations in the history of science. After centuries of progress, after mapping the cosmos, measuring the expansion, understanding nuclear physics and stellar evolution, after feeling like we had the universe more or less figured out, we discovered we'd only been studying the tip of the iceberg. The bulk of the universe, the vast majority of what exists, remains mysterious. We know it's there, we can measure its effects, but we don't know what it is. And yet, despite this humbling ignorance, despite all that we don't know, we've managed to piece together this remarkable story. We've traced the history of the universe back 13.8 billion years to its origin. We've watched it emerge from an unimaginably hot, dense state, expand and cool, forge the first elements, become transparent, light up with the first stars, build galaxies and clusters and superclusters. We've seen it evolve from near-perfect uniformity to the rich, structured cosmos we inhabit. And we've done all this using the tools of observation and reason, mathematics and physics, telescopes and detectors, building on centuries of accumulated knowledge. The Big Bang Theory represents one of humanity's greatest intellectual achievements. It's a testament to our capacity to understand the universe through careful observation and logical thinking. We couldn't be there at the beginning. We can't run the universe in a laboratory. We can't rewind time and watch it all happen. But we can observe the universe as it is now. We can study the laws of physics. We can work backward using mathematics and theory. And we can make predictions that we then test against observations. And remarkably, it works. The pieces fit together. The predictions match observations. The story hangs together consistently. Of course, there are still gaps, still mysteries, still things we don't understand. What came before the Big Bang, if that question even makes sense? What triggered inflation? What is the inflaton field? What is dark matter made of? What is dark energy? How exactly did the first stars form? What is the precise geometry of the universe? Is it truly flat, or is there some slight curvature we haven't detected yet? Will the expansion continue forever, or will something change? These are deep, difficult questions, and we don't yet have answers. But that's part of what makes science exciting. It's not a finished edifice of knowledge. It's an ongoing exploration, a conversation between theory and observation that's been going on for centuries and will continue for as long as there are curious minds to pursue it. Every answer leads to new questions. Every mystery solved reveals deeper mysteries beneath. And that's good. That's wonderful. It means there's always more to learn, always more to discover, always new frontiers to explore. What does the Big Bang Theory mean for us, for you and me, for human existence in this vast cosmos? That's a question each person has to answer for themselves. Science can tell us what happened and how it happened, but it doesn't necessarily tell us why it matters or what it means. That's the realm of philosophy, of personal reflection, of individual meaning-making. For some, the Big Bang story is cold and meaningless, a universe that came from nothing and will end in nothing, with our brief existence a meaningless flicker between two voids. But that's not the only way to see it. You can also see it as deeply meaningful in its own way. We exist. That's remarkable. Against all odds, in a vast universe where most of space is empty and cold and hostile to life, here we are, conscious beings capable of understanding our own origins. We're made of atoms that were forged in stars, and those atoms have arranged themselves in such a way as to be able to think and feel and wonder about where they came from. That's extraordinary. The fact that the universe follows comprehensible laws, that we can understand it through mathematics and observation, that the same physics that describes the first microsecond after the Big Bang also describes the fall of autumn leaves and the orbit of planets. That's deeply meaningful. It suggests a profound unity to nature, an elegance and coherence that's beautiful in its own right. And the fact that we're connected to everything, that every atom in our bodies has a cosmic history billions of years long, that we're literally made of stardust. That's profound too. We're not separate from the universe looking in from outside. We're part of it. We're the universe looking at itself, thinking about itself, marveling at its own existence. There's poetry in that, even if it's not the kind of poetry found in ancient myths. What does this mean for the future? Where is the universe headed? Where are we headed? If dark energy remains constant, a cosmological constant in the truest sense, then the universe will continue to expand forever, accelerating more and more as time goes on. The ultimate fate depends on the properties of dark energy, but the most likely scenario based on current observations is what's sometimes called the Big Freeze or heat ending. Billions of years from now, galaxies outside our local group, outside the small cluster of galaxies that includes the Milky Way and Andromeda and a few dozen smaller companions, will have receded beyond our cosmic horizon. They'll be moving away from us faster than light can travel. Not because they're moving through space faster than light, which is impossible, but because the space between us is expanding faster than light can cross it. We'll lose them. They'll fade from view, their light stretched to wavelengths so long that it becomes undetectable. The universe, from our perspective, will become smaller, emptier, lonelier. Eventually, trillions of years from now, all the galaxies we can currently see will have disappeared beyond the horizon, except for those in our local group that are gravitationally bound to us. The Milky Way and Andromeda will likely have merged by then, forming a single large elliptical galaxy. And that galaxy, or whatever remains of it, will be alone in an increasingly empty universe, surrounded by darkness, with only the ever-cooling cosmic background radiation as a reminder that there was once more. Stars will exhaust their fuel. Our sun will become a red giant in about 5 billion years, expanding to engulf the inner planets, possibly including Earth. Then it will shed its outer layers and become a white dwarf, a slowly cooling ember of extremely dense matter. Smaller stars will last longer, burning their fuel more slowly, but eventually they too will end. The very smallest red dwarf stars might last for trillions of years, far longer than the current age of the universe. But eventually, even they will run out of hydrogen to fuse. The last stars in the universe will flicker out, perhaps 100 trillion years from now, give or take an order of magnitude. After that, the universe will be dark, illuminated only by the faint Hawking radiation from black holes and the ever-cooling, ever-redshifting cosmic microwave background. Black holes will dominate what remains. They'll grow by occasionally capturing stray particles, remnants of stars and planets and gas clouds. The supermassive black holes in the centers of galaxies might have masses of trillions of solar masses. But even black holes don't last forever. Through Hawking radiation, they slowly evaporate, losing mass over incomprehensibly long timescales. A solar mass black hole would take about 10 to the 67 years to evaporate completely. The supermassive ones might last 10 to the 100 years or more. But given enough time, all black holes will evaporate. After the last black hole disappears, the universe will contain only scattered particles moving through an ever-expanding space. Photons with wavelengths measured in light years, neutrinos, perhaps some exotic particles we don't yet know about. The temperature will be an infinitesimal fraction of a degree above absolute zero. Entropy will have reached its maximum. Structure will have dissolved completely. This is the heat ending, the ultimate fate of a universe dominated by dark energy that remains constant. But this assumes dark energy doesn't change, and we're not certain about that. If dark energy grows stronger over time, if it becomes more dominant, its repulsive effect could eventually overcome not just gravity on cosmological scales, but the forces holding everything else together. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then molecules, then atoms. Even atomic nuclei could be ripped apart, and perhaps even subatomic particles themselves. This scenario, called the Big Rip, would happen in finite time, perhaps 20 or 30 billion years from now, ending the universe in a spectacular, violent fashion. Or perhaps dark energy will weaken over time. Perhaps it's not a cosmological constant, but a dynamic field that's evolving. If it weakens enough, if it eventually becomes negligible or even reverses, gravity could regain dominance. The expansion could slow, stop, and reverse. The universe would begin contracting. Galaxies would start falling together. The cosmic microwave background would begin to heat up rather than cool. Space would shrink. Eventually, everything would come together again in a big crunch, a mirror image of the Big Bang, collapsing back into a singularity. And some theories suggest that a big crunch might not be the end. Perhaps it could lead to a new Big Bang, a rebound. Perhaps the universe is cyclic, going through endless rounds of expansion and contraction. Big Bang followed by Big Crunch, followed by another Big Bang. In this view, our universe might be just one cycle in an eternal sequence, with no ultimate beginning and no ultimate end. This is speculative, and there are challenges to making such models work mathematically and physically, but it's an intriguing possibility. We don't know which scenario is correct. Current observations favor the big freeze, the endless acceleration and ultimate heat ending. But we're still learning. Dark energy was only discovered in the late 1990s. We've been studying it for less than 30 years. Our understanding is provisional, subject to revision as we gather more data. New telescopes and surveys will probe dark energy more precisely, measuring how it has behaved over cosmic history, testing whether it's truly constant or whether it evolves. And remember, whatever the ultimate fate, we have time, vast amounts of time. The universe is only 13.8 billion years old. If it lasts trillions of years or more before stars burn out, we're in the very early stages of cosmic history. Most of the universe's existence lies ahead, not behind. We live in a young universe, a universe still full of stars and galaxies, a universe still rich with complexity and structure. Eventually, trillions of years from now, stars will exhaust their fuel. Our sun will become a white dwarf in about 5 billion years, a slowly cooling ember. Smaller stars will last longer, but eventually they too will end. The last stars in the universe will flicker out, perhaps 100 trillion years from now, give or take. After that, the universe will be dark, illuminated only by the faint radiation from black holes and the ever-cooling cosmic microwave background, which by then will be cosmic radio background, stretched to longer and longer wavelengths. Black holes will dominate what remains. They'll grow by occasionally capturing stray bits of matter. The largest ones, in the centers of galaxies, might have masses of trillions or quadrillions of suns. But even black holes don't last forever. Through a quantum process called Hawking radiation, discovered by Stephen Hawking in the 1970s, black holes slowly evaporate. They lose mass, radiating it away as particles and energy. The process is incredibly slow. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate. That's a 1 followed by 67 zeros, an incomprehensibly long time. But given enough time, all black holes will evaporate. After the last black hole evaporates, perhaps 10 to the 100 years from now, the universe will contain only scattered particles, photons of incredibly long wavelength, neutrinos, perhaps some exotic particles, all moving through an ever-expanding space. The temperature will be a tiny fraction of a degree above absolute zero. Structure will have dissolved. Entropy will be maximal. This is sometimes called the heat ending, or the big freeze, or the big chill. It's a quiet ending, a fading away rather than a dramatic conclusion. But this scenario assumes dark energy remains constant. If dark energy changes, other fates are possible. If dark energy grows stronger over time, its repulsive effect could eventually overcome not just gravity on cosmic scales, but even the forces holding galaxies together, then solar systems, then planets, then molecules, then atoms themselves. In a scenario imaginatively called the Big Rip, the universe would literally tear itself apart. Space would expand so violently that even subatomic particles would be ripped apart. This would happen in a finite time, perhaps 20 or 50 billion years from now, ending the universe in a spectacular fashion. Or perhaps dark energy will weaken and reverse. Perhaps it's not a constant property of space, but a field that's evolving. If it weakens enough, gravity could regain dominance. The expansion could slow, stop, and reverse. The universe would begin to contract. Galaxies would start approaching each other. Space would heat up again. Eventually, everything would collapse back into a singularity in an event called the Big Crunch, a mirror image of the Big Bang. Some theories suggest this could lead to a cyclic universe, where each Big Crunch is followed by a new Big Bang, an eternal cycle of expansion and contraction, birth and renewal, stretching infinitely into past and future. We don't know which fate awaits us. Current observations favor ongoing accelerating expansion, the Big Freeze scenario. But we're still learning. Dark energy is a recent discovery, less than 30 years old. We need more data, better observations, deeper understanding. Missions like the Nancy Grace Roman Space Telescope, set to launch in the next few years, will probe dark energy more precisely, measuring how it has behaved over cosmic history, testing whether it's truly constant or whether it changes. Whatever the ultimate fate of the universe, we have time, a lot of time, trillions upon trillions of years, if current observations are correct. The universe is only 13.8 billion years old now. It's in its infancy, relatively speaking. Most of cosmic history lies ahead, not behind. The Big Bang Theory is more than just a scientific model. It's a story, perhaps the grandest story ever told. The story of where we came from and where we're going. It tells us that we live in a universe with a history, a universe that changes and evolves, a universe that had a beginning and will have an ending, even if that ending is incomprehensibly far in the future. It tells us that we are connected to everything. The atoms in your body were forged in the hearts of stars that lived and passed on long before our sun was born. The hydrogen in your cells came from the Big Bang itself, created in the first 3 minutes of cosmic history. You are, quite literally, a piece of the universe that has become aware of itself, conscious matter contemplating its origins. The Big Bang Theory tells us that we live in a universe governed by laws we can understand, or at least partially understand. The same physics that describes falling apples on Earth describes the evolution of galaxies across billions of light years. The same quantum mechanics that powers your phone once seeded the structure of the entire cosmos. There's a unity to nature, a coherence that's both profound and beautiful. The universe is comprehensible. We can understand it. Maybe not completely, maybe never completely, but we can make progress. We can learn. We can figure things out. It also tells us that we live in a universe far stranger than we ever imagined. A universe where most of what exists is invisible. A universe where time and space can stretch and warp. A universe where empty space itself can have energy and can push the cosmos apart. A universe where everything we see, everything we've ever known, emerged from something smaller than an atom 13.8 billion years ago. And perhaps most importantly, the Big Bang Theory reminds us of how much we still have to learn. Every answer opens new questions. Every mystery we solve reveals deeper mysteries waiting beneath. We don't have all the answers. We may never have all the answers. And that's not a weakness. It's a strength. It means there's always more to discover, always more to explore. The drive to understand, that curiosity about where we came from and how everything works, is part of what makes us human. It's a flame that's burned in our species for as long as we've looked up at the stars and wondered. Tonight, as you prepare for sleep, consider this. The light from your lamp, the warmth from your blanket, the air you breathe, all of it traces back through an unbroken chain of causes to that first moment, that initial instant when the universe sprang into existence from nothing, or from something we don't yet understand. You are part of that story. You are made of recycled stardust, atoms that have witnessed billions of years of cosmic evolution. Atoms that have been part of countless stars and planets and clouds of gas before becoming part of you. And consider too that right now, at this very moment, cosmic microwave background photons are passing through your room, through your body, invisibly. These are photons that have been traveling over 13 billion years since the moment the universe became transparent. They were released when the cosmos was just 380,000 years old, and they've been journeying through space ever since, witnesses to nearly the entire history of the universe. Some of them are passing through you right now. You're bathed in ancient light, light older than the oldest star, older than the oldest galaxy. The universe is not just out there, in distant galaxies and cosmic voids. The universe is here, in this room, in your breath, in the atoms that make up your body, in the chemical processes that power your thoughts. You are not separate from the cosmos. You are part of it, intimately woven into the very fabric of space and time. The Big Bang Theory tells us that once, long ago, there was a moment of perfect simplicity, or as close to perfect simplicity as we can conceive. A moment when everything that would ever be was compressed into a point smaller than anything we can imagine. And from that simplicity emerged all the complexity we see around us, all the beauty and diversity of the universe, all the galaxies and stars and planets, all the chemistry and geology and biology, all the life that has evolved on at least one of those planets, all the consciousness that has awakened to contemplate its own origins. It's a story of becoming, of emergence, of the universe unfolding over billions of years, following physical laws, creating structure from relative uniformity, building complexity from simplicity, and eventually, after enough time, producing minds capable of looking back and understanding how it all began. And that's extraordinary. That's wonderful. That's a source of deep meaning, even if it's not the kind of meaning provided by ancient creation myths. You are the universe contemplating itself. You are stardust arranged in such a way as to be able to think about stardust. You are atoms that have become conscious, matter that has awakened, a brief flicker of awareness in the vast cosmic night. And in that flicker, you can know something of where you came from and where you're going. You can understand, at least partially, the nature of the reality you're part of. So, rest now. Let your mind quiet. Let your body relax. You've taken a long journey tonight, 13.8 billion years through space and time, from the initial singularity to the present moment. You've witnessed cosmic inflation stretching space faster than light. You've seen quarks binding into protons and neutrons, nuclei forming in the first minutes, atoms forming hundreds of thousands of years later, stars igniting hundreds of millions of years after that. You've watched the universe build itself, layer upon layer, structure upon structure, from the simplest beginnings to the vast and intricate cosmos we inhabit today. You've earned your rest. The universe will still be here when you wake. It will still be expanding, still be evolving, still be unfolding its mysteries at a leisurely, patient pace. There will be time tomorrow, and the day after, and the day after that, to explore more, to learn more, to wonder more. But not now. Now is the time for rest, for letting go, for allowing yourself to simply be. You have done enough for today. Close your eyes. Let the weight of the day release. Let your thoughts slow and soften like stars fading into dawn. Let sleep come, gentle and natural, like the universe expanding, like time flowing forward into an open future. Dream of stars being born in clouds of cosmic dust. Dream of galaxies spinning slowly through the void. Dream of quantum fluctuations becoming the seeds of worlds. Dream of the universe in all its glory, vast and mysterious and beautiful beyond words. You are safe. You are home. You are part of something ancient and ongoing, something that began 13.8 billion years ago and continues now, in this moment, in this breath, in you. You belong here. You are exactly where you need to be. Rest and know that the cosmos holds you, just as you hold within yourself pieces of the cosmos. Sleep well, star child. Dream peacefully. And when you wake, the universe will greet you, still expanding, still mysterious, still full of wonder, waiting for you to explore it again.